Good morning, Sanjay.
Good morning. Can you hear me?
Yeah. Yeah, maybe you can go to the slideshow mode.
Yeah.
Okay, now it is the presenter view. Okay, now it is fine.
Okay, let me do one thing.
Okay, I think it is a time now. So welcome.
Is it okay?
Now it is a presenter view. So you can swap display.
I'll swap again.
Yeah, now it's okay. So yeah, here you can start. So once I think the PCD is not here today. So I'll welcome everyone to the 9th day of the lecture series. So let us see what is there for you today. So I think we can start, Sanjay. It's already 10 o'clock. So yeah.
Thank you, Sunil. Good morning, everyone, for that 9th class. Heartiest welcome. So we'll be uploading the tutorial for tomorrow's class tutorial soon. So just maybe after this class, you'll be able to see that. But let us start where actually we have left yesterday. So yesterday, what we had discussed about the statistics, okay, photon statistics, okay. And at the end, what we said that, okay, once we understood, okay, the electromagnetic fields are quantized in a small space, a small area of the space, okay. Then whether can we understand the interaction of this light, okay, or quantized light with the matter, because ultimately, unless we have an interaction, okay, that is not useful for any application. Okay. So what we will discuss today, how in a small span of the space, okay, this quantized light can interact. And as you understand, that the space which we are talking about very, very small, okay, and where you can think about an atom or molecule, maximum quantum dots, okay, that can fit it in. So if we can think about the interactions, okay, what that actually we need to know that little bit of the electronic structure of the atoms, which I have discussed at the end part of the yesterday's class. And if you remember that what we have discussed, that we have a example of the sodium atom. Okay, we have a nucleus, we have a core electrons. Two electrons are there in 1s, 2 electron and 2s, and 6 electron are the 2p orbital. And outside this core electrons, okay, sorry, you have that one single valence electron which is roaming around, okay, which is 3s electron at its ground state. So if you can excite by external light, it can go to 3p or subsequent excited state. Okay. So if you have this kind of a picture in your mind, okay, then what we showed that just since we can freeze that code and think about only two level system that atom has, that is it has a 3s and 3p. Okay. Then what we can say that if we assign the 3s is ground G, okay, and 3p is as excited state E, then what we can write that, we can write that Hamiltonian for the atomic system is energy of the ground state times the density for the density matrix for the ground state, plus we'll have energy for the excited state. Okay, these are the eigen energy or eigen values. Okay, times the density matrix for the excited state. So what we can do that, like we can make a reference, okay, and so what we can do that we can make a reference in the sense that the ground state energy we can make a reference and say the energy is zero there. So whatever actually we would be looking for excitation from the ground state, okay, so the difference in the energy is important, and if I set G is zero, then what would happen? Our wave function or will be same, but the Hamiltonian will be written in terms of only density matrix of the excited state. Okay. So here you remember that the kind of basis we are using. So only you have a two orbitals or two states, ground state and excited state, which we are writing in terms of G and E. And they are orthogonal to each other. Okay, so in G and E will be, if you just take in our product of them, okay, they'll give you zero. Now, also we have understood from our earlier classes that we can quantize the radiation field, and if you consider only single mode, here we are just considering only single mode, okay. So then what you could write that Hamiltonian for the radiation is H cross omega, which is omega is the frequency of the light, okay, radiation. At times you will have an operator which is number operator, and we are associating the B operator with the light or with the radiation. So we have B dagger B plus half. And here the basis will be like your number state, okay, will be basis, which can make a complete basis, and n equal to 1 to t. So the total Hamiltonian when we write, okay, what would happen in when there is no coupling between this atom and the radiation field, okay, so they are independent, you can think about. So we can write the Hamiltonian, the composite system, as an addition of the individual identities like atoms and radiation field. Okay. So in that case, what will be happen that I'll be able to write the basis, okay, a basis set for this composite system is I comma n, which is nothing but the I is for the atomic case and n for the radiation or electromagnetic case. So you can write that I direct product of n. So that notation we are writing it in the simpler form is In. Okay, where I can be taking values like G and E, and n can go from 0, 1 to 3. I believe you understood that basis. Okay, so that we have a now basis in a composite systems. Okay, where actually we are just considering that there is no coupling between atom and radiation. So we will be in that frame and take that interactions as a perturbation. Okay. So then what we will be all through using this basis, composite basis, as our reference frame. Okay, and understand the physics coming from the coupling between these two identities. One is atom, another radiation field. Okay. So when we write this total Hamiltonian on this composite basis, okay, In, what I'll get the energy corresponding to the state, atomic state, okay. Then what would happen that I'll have that for radiation field, I have in H cross omega plus half was then half H cross omega, which is vacuum fluctuation we are saying. Okay, so that actually we are just writing it is the E vacuum. Now what would happen? This E vacuum will be there for all the states, all the composite states. Okay, so what we can just neglect because we will be referring to the difference between the energies. Okay, so in that case we can just drop out that E vacuum term all through. keeping in mind that is there always. So what we are just writing, we are writing it as a EI plus in H cross omega I n. Okay. So how this new state, composite state looks like? So you have a ground state, and if you can consider n equal to 0, so you will have the lowest energy state, okay, where n equal to 0, and you have E of G, which also we considered as a zero energy because we are taking that as a reference. Okay. So that will be like a kind of zero energy state. Okay, so G0. And if we have the light which is of frequency omega, and if we consider that if we consider that we have a transitions or resonance frequencies omega naught, and this omega naught, as you understand, okay, this is nothing but the energy difference between the excited state and the ground state without any presence of the photon. Okay, so it is the isolated atoms. Okay, so energy difference between the excited state and ground state. Okay, so that is the frequency, what we call say the resonance frequency. So if you just want to plot, or if you want to draw these energy levels, you can draw that H cross omega naught above the ground level, okay, for this E0. Similarly, if you want to draw that ground state with associated with the one photon, that will come as a here with the H cross omega above the ground state. Now, depending upon the whether small omega is greater than omega naught or small omega is less than omega naught, I'll be able to place the G1 above or below of E0. Okay, so that depends upon that. This is called if you have the light which is coming to the which is actually we would like to work with the atom whose frequency is lower than the resonance frequency. So atom will see that light actually has a lower frequency. That means in terms of wavelength, the atom will see at a, it is a reddened, means broadened. Okay. So once the broadened means that it is reddening. Okay. So this can be told as a, this is a blue detuned, sorry, red detuned light. Okay, where actually your frequency of the light is less than the frequency of the resonance frequency. If your frequency of the light is more than the frequency of the resonance frequency, what would happen? That for the atom, the light would be appearing as a blue light because it will be having a smaller wavelength. Okay, though higher in frequency, but it will be then smaller in wavelength. So that means it will appear like blue. That's why it's called blue detuned light. Okay, which we will use in subsequent next class. Okay. Anyhow, so what you understood that we can shine that light, okay, exactly on the resonance frequency, or you can shine in the below that or above that resonance frequency. Now here what happened, you understood, here we are not shining. Here what is happening? Here you have the electromagnetic field present in some small uh, enclosure, which we are going to say that is a cavity. And in that cavity, when the electromagnetic field is confined, that electromagnetic field is quantized. That means that you will have a defined number of states present inside that confinement or inside the cavity. And depending upon size of the cavity, this frequency of the omega, okay, which is the frequency of the photon, okay, which will be decided. Okay, so that's why. So here it is not that outside we are shining it. Okay, if you have electromagnetic field inside that cavity, that will be quantized, and the photons which are inside the cavity due to the quantization, those will have a different numbers. Okay, you can have the number state 1, number state 2, number 3. Depending upon that, you can assign that composite state. So I believe this is clear. So what I said exactly that we are taking that E wave from Okay, we are setting it as 0 as a reference energy. Okay. Now, once we have this uncoupled system between atom and the field, now let us try to introduce this, okay, the coupling between this atom and field as a first order perturbation to the system. Okay, so we want to see the physics, and first order perturbation will be sufficient to give the physics. So for that, we have to understand how light photon interact with the atom or electrons in the atom. Okay. So what we can say that in presence of the electromagnetic field, let's say we can write in terms of the vector potential A, the kinetic energy of this electron inside the atom will modify in this fashion. We are taking C equal to 1. Okay. And as you see that what actually it does, kinetic energy P square by 2m will be transferred like P minus E by C A. C is constant 1. We are just using that unit. And also we are using the Coulomb gauge where actually the scalar part of the electromagnetic field is 0. So it is actually smaller compared to A. So we are just neglecting that. Okay. So what we have it that we have a new transformation which you have to apply to the Hamiltonian and get the modified Hamiltonian if you want to get the interaction Hamiltonian between light and the electron. So here P is the momentum of the electron and A field is representing the light. So once we square it up, what would happen? You will get term like apart from P square by 2m, which is the kinetic energy terms, and A square terms, which are the self interaction of light. Okay, and what you will have that you will have a terms, okay, which is interaction between matter, which is electron, and the light. That means you will get P dot A terms. So what you will have that you will have E by 2m, and which will be multiplied as the prefactor times P dot A minus A dot P. Now, as you know that P we can write as a nabla with the I is cross factor. Okay, so what we can just see from here that when P dot A is there operating on particular state, so what we can use the chain rule and write it as a nabla dot A operating on psi, so together, and again that A dot nabla operating on the psi. Okay, so that means that we can just use the chain rule and break it up. And again, we can use the Coulomb gauge that delta dot A is 0. And so what would happen that it will appear to that A dot P is coming back. So ultimately what would happen that A dot P terms will be twice appearing and that denominator 2 factor will go off. And ultimately what you will be able to write the interaction Hamiltonian as minus E by M A dot P. So that this is the classical way we just get the interaction Hamiltonian. I think it is clear to you. Now, once this is clear to you, let me just go to that particular mode inside the cavity of the light. Okay. So once you have that light inside the cavity and we are choosing the particular mode, okay, so we are not giving any indices for the mode. Then as we know that we have seen earlier also, so in the vector field of the vector potential, we can write in terms of polarization terms, amplitude terms, and then there will be some term which is operator, which is a dimensionless, which we can write in terms of creation and annihilation of the photon, which are nothing but B and B dagger. Okay, and we'll have 1 upon omega terms. Okay, with some more flip factors. Okay, and the propagation terms. Okay, which will be associated. So if you just see that at the point of the interactions, okay, where actually the photons are interacting with the electron, there we can consider the R equal to 0. Okay, so in that case, what we can see that this interaction Hamiltonian A dot P can be written in this form. So I have now kept all the factors in proper way. So it will be E by M. Now what will have that your P factor H cross by twice epsilon not omega V. V is the small confined volume, okay, and here it will be P dot epsilon. Okay, so that A, what is with vector quantity is living with that, here it is a polarization terms. Okay, and amplitude part actually we are just normalizing it to 1. Okay, so what would happen that you are leaving with the B plus B dagger. So what you will be able to write that in operator form of the Hamiltonian, which you are writing for the interaction Hamiltonian, is nothing but these kind of things, that one P factor will be there. You have a momentum of the electron times the polarization dot product of that polarization, and there will be creation annihilation operator part, okay, which is from the electromagnetic field. Okay, so that's all that our interaction Hamiltonian, which we want to use it in the subsequent slides. Okay, so just pay attention. I would like to request you that this is the form of the Hamiltonian, which we would like to use it as a first order perturbation. Okay, so what would happen now? Just to give you some example. Okay, what happens that when light interacts with the electron in atom, it can absorb or emit. So how do I write this absorption and emission? Okay, sorry. Uh, okay. So what would happen that we can write the initial state. Okay, as you see that initial state is your, let's say I should written A. A can be any state, okay, with a number state n of electromagnetic field. That is my initial state, and final state. Let's say that one of the electronic state in B, okay, to which actually the electric dipole tension is allowed through that interaction Hamiltonian, which I have discussed. Okay, and what would happen? That since I am just going to discuss first absorption, so one photon will be absorbed and atoms will go from the 8th electronic state to the bth electronic state, and that one photon will be disappeared from the system. So we'll have it from n to n minus 1. So as you know that to make it to destroy a photon, you have to operate the A dagger operator. So if you operate, sorry, A operator, annihilation operator, on the number state, you will get a square root of n minus 1. So when we just go from this n to bn minus 1, okay, in that formalisms, okay, in that matrix element, you will be always getting a this eigenvalue. Okay, this it's not this eigenvalue. This is a factor because it goes from n to n minus 1. Okay, so that factor will be always associated with that matrix element. So when we write the absorption matrix element through that Hamiltonian, which we have discussed, okay, what would happen that we'll be able to write, okay, it goes from the electronic part A to B with the P factor which you have just seen, and then what would happen from, as you have seen that from the electromagnetic part, it will be B plus B dagger. And for the here, what would happen for absorption? Okay, it is an annihilation operator. So I should write it here is a B. Okay, so that B actually annihilation operator acting on N will give you the N minus 1. So B dagger will not contribute because it's absorption. So what would happen? You will get a P factor in square root of N because of this transformation of the N to N minus 1. So I believe we have understood how we can write absorption matrix element. Similarly, so here one thing, as I said, that here absorption will take place only when, okay, that you will shine the light, okay, with a frequency which is matching with the resonance light. Okay, that means if you write H cross omega, the energy of the photon which is being absorbed, okay, which will be same as the energy difference between the two states, the initial state and final state of the atomic system, okay, and which we can write as the H cross omega naught, and omega naught is the resonance frequency. So in that case, if you understand that, you can write the emission matrix element also. So in that case, emission process, what would happen that you will get from n minus 1 to n. That means you will gain one photon because one photon is emitted from the system, and the system is going from B to A. Okay, so what you can write it, so you can similar way we can write all the free factor, but here it will be instead of A to B because of emission it will be B to A, and as you see that here B dagger will be applicable, and B dagger applied on the n minus 1 will give the square root of n which is coming. So both the case of absorption and emission, you will be getting that one extra factor square root of n if you are talking about the interaction with the n number of photons or nth state of the quantized electromagnetic field. Okay, and you will have a term, okay, which is which is in the electronic sector. Here epsilon is the polarization, which actually tell you if you just shine the light along the z directions, so you will be doing the calculation of the tension in the z direction. So P will be in your z directions. Okay, so what you, or if you have all the directions of the polarization is there, you will get the calculation on the all directions. So here, whatever the quantity you will get, okay, that of the matrix element, these will be in terms of the correction in the energies kind of things, okay, because it is Hamiltonian terms, isn't it? So what we can write and what is famous in the experimentalist point of view, that they write this matrix element in terms of some quantity which is known as the Rabi frequency. And Rabi frequency omega is nothing but what we write in H cross omega. Okay, and here n factor, square root of n factor is there because we are talking about the n electron system, n photon system. Okay, interaction with the n photon. Okay, so here what would happen that omega will tell that strength of this transition from either the absorption or emission transition, whatever is happening, that will be actually you can quantify using the Rabi frequency. So if you know the Rabi frequency, if you can tell the experimentalist what is the Rabi frequency, they'll be able to tell that what is the strength of this transition, either in terms of absorption or emission. Okay, as you see that both the cases, okay, it is A to B or B to A, and it will be same. Okay, so so Rabi frequency is one of the quantity which actually signifies the coupling between the quantized light here with the electron in the atom. Okay, so what we can write it here, as you see that subsequently that P dot E terms, okay, which we can write in the fashion that we can separate out electronic part, okay, that is A PB, that matrix element. So P operator between that A and B state of the atom dot the polarization terms. Okay, and then what we can use, you can use the Heisenberg's equation. Okay, that P you can write a dx dt. Okay, with the h cross. Okay, so what you can will get that if you use this relation, okay, dr dt. So with the Heisenberg equation, what you will get 1 upon I cross, okay, and commutator relation between H and R. And see, this H is nothing but Hamiltonian for the atom. And these are the states, okay, they are eigenstate of this Hamiltonian. So that means when H is operating either on A and B, you will get back the energies corresponding to that state. Okay, so that what we will get, ultimately we will get A minus EB by H cross, which is the factor which is coming out from this commutator relations. And you will get back this matrix element in the length form. Since it is art dependent, position dependent, it is known as length form. And this is in velocity form, okay, that or momentum form. Okay. So what you see that this is the matrix element for the dipole transition which you will get, okay, electric dipole transition. Okay. So to see that example, let us demonstrate to you. So let's say that electromagnetic field is confined inside a volume. Let's say all the height, length, and width are same 1 centimeter. So it is 1 centimeter cube volume. And let's say that I just the light which I confined it here has a frequency of 50 gigahertz. In that case, what I can write, that I can write this electronic part of the transition matrix element is in terms of that, since it is R is there, so I omega times it will come as a the matrix element of the Z, okay, which is actually we are saying that the polarization is along Z directions. Okay. So in that case, mass m is the mass of the electron. Okay. So what we'll get that, so we know every quantity is here. Okay, 50 is the omega, m is the mass of the electrons. Okay. And what is Z? Z, if I consider that the hydrogen-like system, okay, where Rydberg atoms, okay, where we can tell that Z will be the distance of the atom, okay, distance of the electron, okay, from the center, okay. So here, what we can write it that if you just take the expectation value of Z, it will go by principal quantum number square times A naught. Okay, A naught is the Bohr radius. And if you just put that Rydberg atom like n equal to 50, what you will get, you put all the parameters which is known here, and you will get that radio frequency is like that 100 kilohertz. So this will give some kind of rough estimation how radio frequency can be calculated, or how, what can the figure radio frequency can have. So you have now fair idea. If someone said that radio frequency is this much kilohertz or this much megahertz, okay, you'll be able to tell that what will be the strength of the transition. Okay. So this good idea you should have always in your mind. Okay. Once you understood this one, okay, I'll go slowly because it's actually a lot of mathematics, and all the physics are embedded in the mathematics. Unless it is mathematics is clearly explained, you will not be able to get the physics part. Okay, so I'll go a little slow in the sense that now what would happen that once you understood absorption and emission process of electric dipole transitions, now let us just take the our actual kind of experiment where we are keeping an atom, as we said, having that two kind of energy levels, okay, that atomic energy levels, or electron has the two orbitals, okay, one is grounded, one is excited, and your light is confined inside this cavity. And this cavity is made it here as a Fabry-Perot kind of setup, okay. So what would happen, as we have explained, you will get that composite state like G0, G1, E0, then G2, E1, like that subsequent composite states you will get. Okay. And what will happen that interaction Hamilton, as we have explained earlier, you will get this one. So which, if you want to write down in terms of the two-level system, where you have that G is the ground state and E is the excited state, and if you write that your quantization of the electromagnetic field in terms of the creation annihilation operator B and B diagram, what you see that as we explained earlier, you could write interaction Hamilton in this fashion using the matrix element, density matrix element. But here, as you see that it is not GG, it is actually GE and EG. That's because when you have that electric dipole transitions, okay, between the ground state to excited state, because ground state to ground state, there is a electric dipole transition is prohibited due to the parity conservation, okay, which actually I am not going in, but you reach actually different parity state. That means you need at least different state, okay, to have that electric dipole transition. Now here, what would happen that the G and E are actually, we are saying the 3s, 3p in the case of sodium, as we said, and they are in different parity state, so we can have that electric dipole tension between them. So we can write that if you want to have that dipole transition through this interaction Hamiltonian, okay, between G1 to E0. Okay, so this is G1, this is E0. Okay, which are very close by. If you have the light, which is, if you are making the cavity such that the quantization frequency of the light, okay, that is actually close to the resonance frequency, then these two energy levels, okay, they are very close by. And what would happen that if you want to just check that what will be the matrix element, now you just put that all the terms, that this is the electronic part, this is the electromagnetic part, the light part. So electronic part, you will have a G to E. So here you are putting G and here you put E. This is a Kate and this is a bra from the both side on this GE. Okay, and here also you're putting that E and G from the both side. And what you will see that you will see that because of the orthogonality, so EG and EG term will be cancelled. Only thing EEGG term will be there. Here, in the case of the electromagnetic part, okay, what would happen? You are going from 1 photon to 0 photon. That means you are annihilating. So that means that creation part of the electromagnetic part will be 0. So once you just cross those down, okay, then you can just check it. I would like to advise you, though I have explained, but you can check once again all those calculations. It will be useful for you. So what you will get, that you get h cross omega by 2, and you will get that term which is left over, that EEGG, and you will get 0B1. So what about this one is coming as, this is a 1 because of orthonormality. And here whatever you have 1 photon, B operating on 1 photon, will get 1. So ultimately what you will get back, that the prefactor what you have used in the case of the writing the Hamilton interaction Hamilton operator, h cross omega by 2. So you got that matrix element in terms of the Rabi frequency and which actually you want. So if you can write it in this fashion, okay, you check that that is correct. So you are going to have the correct transition, okay, strength which you got it here back. So what actually we have used, right? So this is the formalisms which we will be using, okay. So we are using that single mode light inside a cavity, and it is interacting with the two level atom. So that is, we are keeping in mind, we have two levels, okay, that uh, and you have a light, okay, which is quantized, and there is a coupling, and this coupling between the light and the atom will be through this transition matrix element. That means this transition matrix element will give you that coupling parameter, which is nothing but the Rabi frequency here. Okay. So I believe you understood that how the coupling term comes. So that is coming from the electric dipole transition strength, and which you can write in terms of the Rabi frequency. So here you see that to choose a single mode, you have to have a cavity. Okay. Otherwise, you will have all possible modes. Okay. You have a very confined, very precise cavities. Okay. So which we want to choose it here. And thing is that here the cavity also sometimes we say that is a resonator. That's because what would happen, lights are filled, or the photons which are created inside, okay, they can bounce back and forth, like they'll reflect it and make a standing wave kind of things. So that's why they also call it as a resonator. Okay. So to have the proper resonator, okay, or the cavity, we should have some parameters. What is that parameters? Okay, as we understood, we are looking for some interaction between light and matter. So we should have the system where actually it actually can be favorable to the better coupling strength. Okay, so it can happen that you can have the coupling very weak. That's because if you take the atom which is very small in size, okay, and if you want to see the interactions, generally coupling strength will be very small. But in that case, what you can do, as I explained, you can consider a Rydberg atom which is having a bigger size, okay. Then you can think about the, or you can just estimate that you may have the larger coupling strength. Second thing is that once you have that atom in the excited state, there is a probability that it can spontaneously emit. So a spontaneous emission you have to control. Okay, there is a person, there is a way to control. Experimental does also that once you have the light inside, you need that light to be protected. It will be like a adiabatic process. Okay, so though no light can come inside, no light can go outside. So we want to just control the loss rate of the light, which actually one can write in terms of a factor like kappa. So these are the parameters which are actually classification for the your resonator. And depending upon these parameter values, okay, you can judge whether the resonator is good or bad, whether the resonator has a strong coupling or weak coupling. Depending upon that, different physics you will get. Okay, so so as you said, in generally, as I said that in generally that if you have a normal atom, you have a very weak coupling, and weaker than this the rate of spontaneous emission or the loss rate of the electromagnetic field. So in that case, the French guru, Serge Haroche, okay, who got a Nobel Prize, I think you know that a few years back, they had developed a new technique, and that's not new. They knew that if you can use a Rydberg atom, whose actually the electrons are residing on the higher orbital, like n equal to 50, 51, 55, very large number of the large value of the principal quantum number. There you could get the dipole moment is very strong compared to the normal atom. It's around 1,000 times more than that. So it is written 1,250 times. Okay, it is a very large compared number. So in that case, what would happen? You will be expect that you can get that very strong coupling. So if you can choose this kind of atom, okay, the Rydberg atom, and choose two different values like different principal quantum number and S and P, okay, then what would happen? S and P orbital or opposite parity orbital, then that will be ideal for this kind of a experiment. Okay, for the cavity, we have to make some setup. Okay. So thing is that we have to somehow, as I said, that the gamma have to be controlled. So there is a technique they have used, which I am not able to explain that to stop the spontaneous emission rate or to minimize the spontaneous rate. But one can do that. I can explain you easily that how to suppress this the radiation loss. Okay, the electromagnetic light loss from the cavity. Okay, so for that they use the very good fabric cavity. Okay, so spherical in the shape. So they use a mirror. Okay, the mirror is made of some coating. Okay, they have a coating on the mirror, the superconducting niobium, and it is known that niobium have the low dissipation. So that will be very useful for this kind of a cavity. Once you have make a cavity, now you have to bother about what is the size. And as you know that this size determines what kind of a frequency that photon has inside the cavity. Because as you understood that the photon, whatever the frequency it has, can be actually related with the volume of the cavity. Okay, so what we can have that we can make a size profile so that we will be able to close to the resonance frequency. So we can our this photon frequency will be close to the resonance frequency, and that difference between these the omega and omega naught are known as detuning, which actually we write in terms of the parameter like delta. Delta is nothing but omega naught minus omega. It can be positive or it can be negative depending upon blue detune or red detune light. Okay, so in absence of that coupling, that atom field coupling, so what would be our Schrodinger equation in time dependent form? Okay, so what would happen that we have that atomic part of the Hamilton, we have radiation part of the Hamilton. Now we just write that basis state in the composite system, either Gn or En. Okay, so in the case Gn, what would happen? I get back that G energy, the atomic energy of the ground state, we set it 0. So only that I'll have the energy of the number of photons. So that is nothing but in H cross omega. That is we as a eigenvalues for this operator when we consider the Gn is the eigenstate. Similarly, if we have that En is the eigenstate, okay, what would happen? We will have that h cos n omega, as that is the energy of the photon. Okay, but additional things we will have that we will have excited state energies, okay, which will be added with that. Okay, so we'll have h cos omega naught will be added with the photon energies to get the total eigenvalues for the eigenstate En. Okay, so I believe you have understood how you have got these eigenvalue equations. Okay, so we have to understand this thoroughly. Once you understand, then what we can write, we can switch on the coupling. Once we are switching on the coupling, okay, what would happen now? We have that possibility between transition between one state to another state, as we have understood. Okay, so and this transition depends upon the Rabi frequency, okay, or coupling length, coupling strength, okay, and which I writing is omega 1. Okay, or let's say that we are having that one photon cases. So if we can write omega n for the n force, so I should have written omega n because we are writing GL form of n. So this is between n and n prime. So omega 1 is, you can think about just another Rabi frequency corresponding to this transition. So in that case, your problem will be clarified. Now, what would happen? So as you see that we have the non-zero matrix element, okay. So our I and ij should be having some kind of opposite parity state, okay. And as you saw that a CSTP, like we can assign that G and E, okay, or E and G. Those will be the proper state for I and J here, okay. And in that process, okay, when it goes from one state to another, it either absorbs or emit. Depending upon that, your n will be decided with the n prime, whether it will be n prime plus 1 or n prime minus 1. Okay. So what we'll get that you will get the particular choices of I and j and particular choices of n and n prime. So once you have understood, so let us write, since we have already got our basis here, okay, G1 and E0, or I can write it as Gn and En minus 1. So let us write the matrix element. So if I write a matrix element in terms of the Rabi frequency, as you know that, as you remember, Rabi frequency for that presence of the n photon, okay, will be square root of n times of the Rabi frequency where the one photon was present. Okay, so what would happen that I would say omega 1, what we wrote it here, I am writing it as square root of n times omega. And the rest of things are as it is, okay, that we'll have a h plus omega by 2 is the strength of this transition. When we will have this one, okay, gn to en plus 1, okay. So in the other cases, we will have an n plus 1 factor will come. So what would happen? I think I have written it wrong way. This side it will be n plus 1, this will be n. Okay. So this side it will be n plus 1 and this side it will be n. So that's why it is coming n plus 1. Okay. Anyhow, so what you got it now, you see that we are able to get coupling between these two states, Gn and En minus 1 or Gn plus 1 En. I should write En. Okay. So what would happen that if you see in the picture, depending upon your frequency of the quantized photon, okay, if it is close to that resonance frequency, what will happen that you will get this transition between this state to that state is strong, and you will get a doublet form of this. Similarly, you will get a doublet form of G2 with the U1, G3 with the E2, like that you will get. But as you go higher and higher state, your strength are actually reducing. Okay. So that you have to understand. So we got that almost degenerate states, okay, by choosing the proper size of the resonator or cavity, and which is having some kind of frequency which close to the resonance frequency of the atom. So once we have the degenerate states, okay, now we'll be able to appreciate this time independent coupling. Okay, that's why what we can write that in the subspace of this Gn and En minus 1. That means if I consider n equal to 1, so we'll G1 and E0. What we can write it, we can write it in this fashion that these will actually emit, this will be corresponding to the emission, this will be corresponding to the absorption. So this will annihilate a photon, this will be creating a photon. And depending upon number of photon, your gamma So the total Hamiltonian. Now, in presence of this coupling, okay, well, if you can want to write, okay, you have that you have the uncoupled energies, and you remember uncoupled energies is in omega for the nth state. So if I take that, if I take the Gn, so this will be n omega. For n, if I just consider this one, okay, so this one will be just omega here because G1 is considered. Okay. And what would happen to that the excited state? Okay, excited state energy. So this one will have energy. G1 will have a energy of just one time omega. Similarly, in that basis, okay, E0 say n equal to 1, E0, what would happen? You have a n omega, that's omega times you will have, you have added up with the detuning part, delta. So that will be in diagonal part. Okay. So I think just try to understand again. So the diagonal part will give you the uncoupled energies of these two states which are involved. Okay, so we are just writing this Hamiltonian, total Hamiltonian in this subspace G, N, and En minus 1. Okay. So that means just consider from the picture n equal to 1. So that is G1 and E0. Okay. So if you consider what would happen, you will have that H, the total Hamiltonian will be having H cross times, you will have a term, okay, n is 1, so it is omega. And what happened in this other state, that other state E0, E0 will have that n omega plus delta. N is 1, and so it will be omega times H cross plus H cross delta. Delta is a detuning frequency. Okay. So what you got it, the diagonal terms from the uncoupled system energy eigenvalues. Okay. And the coupling term will give the non-diagonal terms. Okay, that is coming from this coupling strength. Okay, so square root of n h cross omega by 2. And so what you got it here. Okay, so you got that. Just don't bother about that superscript also. So so that you get it from this for this Hamilton. So I believe you have understood the formation of the matrix formation of the Hamiltonian that is in this space. So that means that if you take these terms, this term is nothing but this Hamilton with respect to Gn and Gn. This term is that total Hamilton in terms of En minus 1, okay, and these are the exchange terms, that is between Gn to En minus 1 and En to En minus 1 to Gn, okay. So that is the off-diagonal terms. So once you have understood this one, let us see that what will be the solution. So just consider that each doublet, okay. So we got this Hamiltonian, and now we just diagonalize. If you diagonalize, you will get eigenvalues. And eigenvalues looks like this. So what you will get? You will get that some kind of extra terms which you are getting. As you see that this is n times. So let's put all n equal to 1 so that we can just see it from this picture. If you put n equal to 1, so it is h cross omega plus delta by 2, which is the halfway through this division or through this difference. Okay, so that if you just took the halfway to the difference, from there is a splitting. Okay, splitting is of this amount. Okay, there is half square root of this goes by that the omega square. Omega square is nothing but the strength of this coupling between these two states. Okay, so that is square quantity. So that is positive quantity, and delta squared. So it doesn't matter whether I use blue detuned or red detuned, whether delta is positive or negative, it is delta squared. So that whatever quantity you will get is a positive definite quantities, okay? So there is no imaginary part here, okay, ultimately. So you'll get either above to this mean value as a central value, the halfway to the difference, or below that halfway difference. So you'll get the splitting in the energies, okay? So because of this coupling, okay, so I hope I have explained that you got that energy difference between or splittings, okay, in the coupled space, okay. So you will get effective picture, and you will get two states, new states, okay, which is a linear combination of these two uncoupled states, okay, E0 and G1. And the way you can write in normal form, actually, when you write that superposed state, okay, you write it with some cos theta, sin theta, and theta will give the strength of the coupling, okay. So then what you'll get that you will be able to write psi plus 1 or psi minus 1, okay. So depending on, you will get that it is G1 and E0, G1 and E0, but this coefficient will be exchanged between these two. Okay. So this is the normal way we can get the coupling superposition between the two states. Okay. And this cos theta n actually will tell us the how the state. So what we get it here, if you see in terms of picture, you see that for the E0 and G1, we get the two different state or splitted state, okay. The doublet actually now splitted further. You can think about that this is psi plus 1, psi minus 1, okay. And these are the new states, okay. Cos theta n G1 and sin theta 1 0, like that you can write it. So what will be the value of theta? Theta n, as you understood, you can get it from easily from this from the in the nominal terms, okay. That is omega 1 squared over n by delta. Okay. So delta terms omega will come. Okay. So that is very interesting term. So you have to just work with this one and you'll get this term. And once you get these terms, now you see that how this coupling between these two, that E0 and G1 is happening, okay, and which will give you that the new eigenstates, okay, for the Hamiltonian, okay. So that new eigenstate for the Hamiltonian, okay, which you are writing is psi plus 1 and psi minus 1, okay, those will have that coupling, okay. We obtain them because due to the coupling between that these two states, okay. And this coupling, okay, is dependent on not only that coupling between these two, that the transition strength between this G1 and E0, it also depends, okay, how much is the value of delta, how far. So as you see that if delta is very small, okay, so your theta, what would happen that delta is small means that this quantity becomes large, okay, for any particular value of n, okay. So once this is large, that means theta will be also large. Okay. And if you make the delta is very, very large, okay, what would happen? That you'll be getting that almost close to the resonant frequency. So once delta is very, one delta is very small, I should say. One delta is very small, okay, we will get almost close to the resonance energy. That means you are bumping to the resonance condition. Once you are bumping to the resonance condition, it's like a switch and a switch up. You will get the system in excited state. That's all. Okay, if you are getting the excited state, it will be like a then from there you will get the spontaneous emission. Okay. But if you have a little lower than the resonance frequency, what would happen that you will have still coupling between these two, and that coupling depends upon your that detailing factor. Okay, and if delta is large, okay, if delta is large, as you see that this term has become very small, that means theta n becomes very small, and that means this coupling will be very, very small, and which will say that if theta n is 0, okay, theta n is when 0, that means this is 1, this is 0, this is 0, this is 1. So you will get back that uncoupled state Gn and En minus 1 when delta is very, very large. Okay, so you get back the states. Okay, so if you want to see that, okay, I'll show in the next slide how this coupling is varying with respect to delta. Before that, one more point which I want to stress it here is that if we can by some means of a delta, okay, what you see that we can get uh, um, sorry, I think I did wrong thing. If delta equal to 0, sorry, yeah, it was right. Okay, if delta equal to close to 0, sorry, so we'll get almost infinite. Okay, so that we'll get theta 2 theta n is pi by 2, and theta n will be pi by 4. Okay, so then what would happen that when theta n pi by 4, if you put it back, all those coefficient will be 1 upon root 2. So what we'll get that you will get that psi plus and psi minus state is nothing but 1 upon root 2 gn, either plus or minus, okay, en minus 1. Now, these you see it like in this form, what you realize that now if you want to just separate them, we have to separate the atomic part, okay, from this state, okay, you will not be able to separate them. Because what would happen, suppose I want to measure, so the electronic state, either I have to get in the ground state or excited state. But once I just get in the ground state, the system will collapse to the nth photonic state. Or if I just observe in the excited state, system will collapse to the n minus 1, okay, photonic state or electromagnetic state. That means that the superposition of these the different number states of the electromagnetic field, okay, that is lost. Okay, so that the superposition was lost, and that means that if you measure either of the system, either electromagnetic field or atom, okay, you will break the superposition. So that's why this is called entangled state. Okay, so entangled means that you will not be able to write them as a cross product, okay, a direct product of atomic state times the electromagnetic state. But other way to say that you will not be able to find them, okay, as as either of them, okay, the atomic state or either the electromagnetic states. Okay, so that's why it's called the entangled state. And if you see that that amount of entanglement is here. Okay, so this is that probability of finding this or in this state is Gn is half, and probability of finding En minus 1 is half. So this is say that for choosing the theta n, which you are choosing by which? By using the delta values, okay? By choosing the delta values and proper choice of omega, you can make it that the proper value of theta n, and what you'll get, you get the maximally entangled state. You can get maximally entangled state. And this is the one which is very much useful in the future quantum technology programs, okay? So whatever going on around the world, okay, quantum computing, other things, this entangled state, if it is maximally entangled, is very good, okay? You can use it for different purposes, okay? So in the last slide, what I want to see for today's, okay, because I will have some more slides here on the same system, okay. But just I want to show that how, so this we got entangled state, how this entanglement, okay, it depends upon a delta, the detuning part. So let us show that this is the x-axis is delta. As I said that if you go for large value of delta, if you remember the expression, if you go for large value of delta, okay, what would happen that this term will be 0 and theta n will be 0, and you'll be able to separate them out either in Gn or En minus 1. So what would happen that so either theta is very, very large or means positive side or negative side, you get the separation between these two, there's coupling will be there. But as you bring the delta close to 0, the two states will be coupled, and that will be maximally entangled when delta is almost close to a 0. So what you understood that using this kind of systems, coupling between the light and atom, we could get one of the beauty of the quantum system, that is the entangled state. Okay, so This coupling between the two-level atom with a single mode light, also known as Jens-Camis model, name given after their proposals. Okay, so they have proposed. Okay, there's a paper written by them. Okay, on 1963. Okay, there's a proceedings of IEEE. Okay, if you interested, just look at it. Okay, so this is the famous Jens-Camis model, which is used nowadays in many kind of experiments for quantum technology. I'd like to stop it here and try to explain it more realistic scenario where actually you have a quasi-classical light. Okay, in that case, actually quasi-classical means that laser light. Okay, inside a cavity, what you do or what you get, and you see the beautiful phenomena from that. So that with some amount of laser cooling and trapping will be discussed. Okay, and last class, that is tomorrow. Okay, so since we don't have much time, we will not be able to discuss in a length laser cooling and trapping, but maybe in subsequent some other time, okay, if we get chance to discuss, we'll discuss thoroughly. So I'd like to end it in today's class here. I would like to have some questions answered if you have. Thank you for your attention.
Okay, so please send your questions in the chat box. Okay, there is a question from David Joseph. Please explain the significance of Rabi frequency.
Okay, let me go back to that slide again. Where actually I have discussed the Rabi frequency, and from there I. Sorry. No. Yeah. I think I have just typed. Yeah. Okay. So this is your Rabi frequency. As you see that, what we have written. We have written that the transition matrix from the Bn-1 to An. Okay, and that is the matrix element for interaction Hamiltonian. So interaction means if you just consider, let's see the figure here. So here you have a atom having the two states A and B, and we are saying that okay, here it is okay, going from B to A. That means the atom which is in excited state, okay, emitting that one photon and going back to the A state, the lower energy state. Okay, so what would happen that suppose it has n-1 electron, okay, due to this emission, it actually give you in the system one extra electron. So from n-1 you go to the n state. So now if you write that, what you will be able to write, because as you have seen that the way we write that interaction Hamiltonian, you will be able to separate out, okay, electronic part or atomic part and the electromagnetic part. Okay, if you separate them out, so what would get that from the electromagnetic part, you'll get a square root of n, and from the atomic part, you'll get that transition like an isolated system, okay, from B to A. Okay, and this P, as I discussed, this you got it from the interaction like P dot A terms. Okay, so that this is a dipole transition, okay, electric dipole transition, which actually I have subsequently showed that you can write in terms of the position also. Here it is written in terms of momentum, which is known as velocity gauge, and also you can write in the length gauge that in terms of position. Anyhow, so what you got is this quantity will say that how this transition from B to A is actually possible, or what is the strength of this transition. This is independent of whether you have the whatever ambience electromagnetic field is there. Okay, that you can have another state, you can have n-1 state, whatever state is there. But that you just forget it out. If you have isolated atom, okay, and you just tell that okay, this is the strength of the transition from B to A electric dipole transition. Okay, that transition, if you want to quantify So this is the one which you are quantifying with the some kind of a frequency, because as you understood, this is nothing but a Hamiltonian term. Hamiltonian means energy. Energy means you can write h cross time frequency. That frequency, which actually corresponding to the transition strength, okay, the matrix element strength, okay, that we are writing in terms of h cross omega. Okay, so that's why this omega, okay, is nothing but, okay, the radio frequency, that is the nothing but the strength of the electromagnetic tension, irrespective of where you are putting the atom, whether you are in energy state of the electromagnetic field or in -1 state of the electromagnetic field or 0 photon of the electromagnetic field. Doesn't matter. So this is the purely intrinsic to the atom. Okay, so that will tell that strength. I believe it is understood.
Okay, so now there is another question from Rashid. If the system interacts with the temperature bath, what effect does it have on the Rabi frequency?
Very good question. As we have seen that, okay, these if you have a temperature, okay, as first of all, Rabi frequency, as I said, this is intrinsic to the atom. It doesn't matter whatever the light you have outside, okay, the which state. Similarly, if you have a temperature also, okay, it is independent of the temperature. Now, what would happen that in place of temperature means that you can have a thermal radiation. Okay, that means you have to consider that the thermal fluctuations in the system. Okay, if you consider thermal fluctuation, okay, you have to treat them separately like we are treating electromagnetic field. Okay, and as you see that when you have external electromagnetic field, okay, it is in quantized form, and if you are considering any number state of the electromagnetic field, that radio frequency is multiplied by square root of n. Like that, you will have an extra factor will be multiplied once you have the quantization of the thermal fluctuation, okay, or thermal radiation. Okay, if you have a quantization of thermal radiation, okay, then you will have a one extra factor. So, but whatever omega, that isolated atom omega, that will be intact. That will not be changed. Only thing, whatever the external things, that will be coming as an extra factor to that isolated atom radio frequency. Got it? I think he has got the answer.
Okay, hopefully he's okay with the answer. So is there any further question? Yeah, it's okay. Now, is there any further question? Please send it in the chat box. I think there is no more questions. Okay. So I think then it is a time to conclude for today.
Thank you.
Yeah. Thank you, Sanjoy, for another wonderful talk. And then, of course, IT team and the student volunteers. Also, the participants I would like to thank. Yeah, I would suggest you ask more and more questions so that it will be more interactive and you will be able to understand better what is covered in the course. It will be very good for you and also for others. So today there is no more sessions. Tomorrow there is a lecture. That is a last lecture in this series, and then there is a tutorial session at 3 p.m. Okay. So thank you everyone. So let us close this session for today. Okay, thank you, Sanjoy.
Thank you, Sunil.
Okay then, bye.